with the what happens down in the cellular level, you can start to figure, you got a blood vessel here. That's probably be a capillary bed because we're talking about glucose being pushed out of it. So, and that happens down in the capillary level. And then we've got our cells here. Let's make those guys brown here. Right? See, kind of get our cells out here. All right. So what happens is, and we've talked about this when we were talking about fluids and electrolytes, the shifts. What happens is through hydrostatic pressure, the pressure created by the heart, it's coming out here. These vessels, when you get down the capillary bed area, are just one layer thick. The endothelium is all you have. You don't have the muscular layer, and you don't have the basement layer. You just have this endothelial layer here, and it's one layer thick. So you get this pressure pushing this blood through, and the things that are in it that are small enough to squeeze through the slits in these guys here, they will get pushed out with fluid. So they'll come down here, hydrostatic pressure is pushing it out, it ends up getting pushed out of there. So let's go ahead and make some glucose. Let's make it blue. Get some glucose in here, and it gets pushed down into here. Right? Glucose goes in there by diffusion, but it has to be facilitated. So remember when we were talking about the different types of movement of electrolytes and things moving across membranes, facilitated diffusion was one of them. This one here, it's going to diffuse just by the power of things wanting to go from an area of greater concentration to an area of lesser concentration. So that diffusion will not go across these cells unless these cells become permeable to the glucose, right? So you got this glucose coming here. It's moved out into the interstitial cells. Something has to make these permeable because in normal state they are not. And what they have in here, let's take a look here at this cell right here. All right, I just circled that. Take that baby right out here. And now I'll put this cell here. And I'm going to make him black. What the heck? I think it'll show up there on that thing. So now you've got this here. I'll look and see. I don't have a glare. I got a glare on this board. I should have done this more in the daytime when I didn't have to turn the lights on. But anyway, we get this guy here. That's this cell, right? I took this cell, I took it out here just so I could draw on it and not have all that other crap in the way. So now you got to remember, this is a three-dimensional thing. I can only draw two-dimensional on the board here. So we've got these here, and these guys here, I'm going to call them insulin receptors. Well, I'm going to call them like I made that up. They are insulin receptors. And like I said, this here is a two-dimensional picture. Think of this like this guy here. I drew him round, so if you were really looking at him, he'd look like a basketball, right? You're round, an orb. So you got these all over on it. So these insulin receptors, what happens is you've got insulin coming down here too. It's been released by the pancreas, right? We talked about that. So insulin's coming down here. It gets pushed in there too. These receptors, they're insulin receptors because they are receptive to insulin. Let's make these insulins. If you take that insulin there, bring him out here and take a good look at him, we'll say that he's shaped like a triangle. So he'll fit right in to that spot, right? They'd fit right in there. Well, in a healthy person, this triangle is going to come up here, or this insulin is going to come up here and going to fit right into that receptor. So it fits into the receptor, and what it does is it activates the entire membrane. It makes this entire membrane permeable. So the membrane is permeable to glucose now because the insulin fit into the receptor, and now it can cross into that cell. And that happens in all of these cells, right? So then your glucose comes down, moves into the interstitial area by hydrostatic pressure, and with facilitated diffusion, it moves into the cells, facilitated by insulin. So now it moves into the cells, and the cells are able to use that glucose for energy now. So that's how the glucose gets into the cells. And we were saying that this here, let's say if this was a muscle cell, right? It goes into the cell, and the muscle's going to use that for energy. We got to remember too is that in the liver, it's converted over to glucagon or glucogen, and it's stored in there. So that's what the insulin ends up doing. That's how it gets it into the cells, and it gets it into the liver cells and stores them there as glucogen, which we know that we should know that then glucagon comes along and it will break down that glucogen and back into glucose and put it back into the bloodstream when the blood sugar levels get low. Okay, we're going to talk about glucose regulation. Um, our glucose needs to be for ultimate health. Our glucose should be between 70 and 110. Some will say 70 and 120. Some will say if it's between 110 and 120, our glucose level, that you're pre-diabetic. If you're over that, and this is fasting blood sugar. That's the only one. I mean, you can expect to be over that when you're not fasting. Right after you've eaten a piece of pecan pie or something, it might shoot up to 145, 150 or something, but your system will bring it back down, and we'll talk about how it does that. But we have to stay in this. But our range as far as fasting, when I say fasting, what that means is that you'll take it after they've not eaten for 12 hours, right? So a person will be told to come in first thing in the morning and have their blood glucose drawn before they eat. That way you can get a fasting glucose level. Fasting level should be between 70 and 110 or 70 and 120. Different literature kind of will say some different things on that. Why does it have to be in this range? Why is it so important that we keep our blood glucose in this range? It's a pretty narrow range, really. High blood glucose can do a lot of damage over time. Glucose is actually toxic to the endothelial cells, the cells lining the inside of our blood vessels. So it's actually toxic. So we need glucose because we need it to be in our system to feed our cells. But at the same time, we don't want any more of it than what we have to have. So the consequences of damaging the inner lining of our blood vessels. Well, the small vessels are going to get damaged first, right? They're smaller, that inner lining is more vulnerable. You'll get a lot of damage. Peripheral circulation, circulation like down in your legs, far away out, out there. So you get circulation problems out in your feet. So what's that going to lead to? It's going to lead to problems healing, neuropathy, right? Neuropathy means that you might get numbness, tingling, or pain down in your feet. And you're getting that from the nerves, from damage to the nerves. Neuropathy, right? Nerve is the near part, apathy. The pathy part is the disease, so disease of nerves. So anyway, so that's one of the things is your distal circulation, neuropathy, and circulation, poor healing of wounds and things because you're not getting the circulation to those areas. A lot of people can get foot ulcers and stuff, and because of the numbness, they don't even know they have them. It's numb, and then then it doesn't heal well. Both of those are things that are happening from their diabetes. Yeah, so when you get a foot ulcer, right, you're getting it because you have poor circulation to the area, a result of the diabetes. You don't even realize you have it because your feet are numb, so a result of the diabetes, right? So it gets worse, it gets infected because you're not getting circulation to the area to help it heal, so it doesn't heal well. All of that is results of diabetes. Another problem is, small vessels that innervate the eyes, right, can affect your vision badly. People can go blind, and people do go blind because of the damage done to the eyes, to the retina from diabetes. Kidneys, right? You also have circulation to the kidneys. The glucose is actually toxic to a portion of the nephron. In the nephron, you have the glomerulus, and there's a portion in the middle of that there that the glucose is actually toxic to. So kidneys, your heart, right? You can get damage to your blood vessels in your heart, so it can lead to heart problems. So we've been talking about high glucose, right? You get the high blood glucose levels, it can cause all of those problems that I was just talking about. That's all from having high blood sugar. Now, hyperglycemia, right? Hypoglycemia, low blood sugar, is a different story. It causes problems too. Most of the time when we're dealing with hypoglycemia, it's a result of treatment for diabetes, right? So you're taking insulin, right? You give yourself a shot of insulin so that your blood sugar and stuff can come down. But if you don't eat, then you end up with hypoglycemia, right? Then you have to give some glucose to get glucose back in the system. And why is it so important that you have glucose in the system? Well, for one thing, every cell in your body needs glucose. That is what our cells use for energy, is glucose. The most dangerous part of hypoglycemia is that your central nervous system, mainly your brain, needs a constant supply of glucose being delivered to it. It needs glucose coming in and being delivered to it constantly because it doesn't store it. Our muscles, it takes glucose in, right? When it gets the chance, it takes the glucose in, and it makes this ATP that it can use for energy, and then it's got it there. But not your brain. Your brain needs it constantly. It uses what it gets in, and it doesn't store it. Right? No stored energy in your brain. So it needs that constant supply. So you can't let your blood glucose level go down to zero. Right? You just can't let it get down like that, because as soon as it gets down low, below 70, below 60, below 50, this person's going to start not being able to think right. They end up, and if it gets too low, they'll end up comatose and die. Very serious deal. So I've got a diagram here. Hopefully we can see that on your thing there. Let's see if I can. Right, so we've got this Pac-Man looking head up here, a candy bar, right? Stomach, right? The intestines, the pancreas. I drew over here and drew it nice and big because that's really what we're going to be talking about. The pancreas and the liver. And this here is, this red is representing portal circulation. So it's part of our circulation. It's the part of circulation that goes from our intestines to our liver. It's kind of separate from, right, we got our systemic circulation. It comes out and goes out into capillary beds and feeds all of our muscles and all of our other organs and stuff, right? And then it comes back up to the heart and goes to the lungs to get oxygen again and goes out and does it again. Well, in this case here, this portal circulation is a little bit different, because we get circulation coming in to the intestines, then it comes out, right? It's the capillary beds in the intestines, picks up whatever the nutrients and stuff that we've eaten and everything, comes on into the portal circulation, ends up in this large portal vein, and comes up to the liver. And then the liver does its detoxifying and stuff, and then it goes back up to the heart, and then goes out to the body. Really good reason for it to be that way, and that is that when it's going to the liver, everything that we eat a lot of poison stuff, right? With a lot of dirty crap, a lot of stuff that we shouldn't eat, right? Probably historically, cavemen and stuff ate whatever we got our hands on, right? Well, would have killed us if it wasn't that our circulation is set up this way, that we have this portal vein here that takes the stuff that we've eaten and it comes over to the liver, and the liver detoxifies. Says, hey, that's no good. Adds a couple chemicals to it and makes it so you can pee it out, puts it out in the blood, and then you can get rid of it, right? That's just something that the liver does, way beyond this class or way beyond my knowledge to try to teach you how it does that, but I just know that it does do this, that detoxifying of things that come in. And another important thing that it does is what we're going to be talking about here. It's regulating blood glucose. So that's the portal circulation. And now we've got the pancreas here. The pancreas sits right, it was actually behind the stomach, but I can't draw it behind the stomach. I had to pull it over here where you could see it. And you've got your pancreas here, and it has endocrine and exocrine functions, right? It's both an endocrine and an exocrine gland. An endocrine gland means that it it releases its products into the bloodstream, right? That's the endocrine. The exocrine means that it releases it to the outside of the body, right? Like a sweat gland releases it to the outside of the body. And you might say, well, wait a minute, the pancreas is releasing this into the duodenum. Actually, you got the stomach here, then you got the duodenum down into the first part of the small intestines, the duodenum. So it comes down into here and then goes through the intestines. But releasing its enzymes into the duodenum is considered releasing it to the outside. All the way through my mouth, all the way down through my intestines and out the anus there, all considered the outside, right? Because it's considered on the surface. And the way you got to think of it this way is think of like a donut, right? You got a donut here, and you got the surface of the donut. When you go inside the donut hole part, right? It's still got the surface in there. It's inside the donut, but it's still in the surface. We think of this as the inside of the donut, all the way down through there. So it goes down through there, but it's still, when the pancreas is releasing things into it, it's considered releasing it onto the surface. So that's why we call it an endocrine and an exocrine gland, because it does have both of those functions. And then we got the liver, right? And the liver is what is going to do the storing of glucose. So now we'll talk about how this happens. Person eats this candy bar, boom, comes down into the stomach, goes through some of its digestion, comes down here and gets absorbed into the bloodstream, right, through the portal circulation, the portal vein, and it heads on up to the liver. On its way to the liver, and I drew this so that the portal vein that I drew, and this isn't anatomically correct at all, of course, I hope that you realize that, but as it's coming up, I drew it kind of going, brushing against the pancreas there, just to represent the fact that the pancreas is going to taste a little bit of this blood in the portal circulation. So it gets absorbed, and the pancreas is going to get to taste it right away. Right? It's going to have to go through the whole body to get to the pancreas. Boom! Right away, we find out is there's something sweet coming in. Right? He eats this. Boom! 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 Comes through there. Says, "Hey, something sweet's coming through. We got to take care of this." And what it does is it releases insulin from the beta cells. Now, that's something I didn't tell you. Is here in the pancreas, you have these little aisles here that I got. They're called the islets of Langerhans. And in the islets of Langerhans, you have alpha and beta cells. You have delta cells too, but we don't need to talk about those. But so you got the alpha and beta cells in here, and so now what's happening is this candy bar was eaten. It was absorbed. It came through here. Pancreas tastes it. Says, "Well, that's sweet. Let's release some insulin." And the beta cells in the islets of Langerhans, so the beta cells of the pancreas release insulin. And the insulin comes right away. So before this spikes up really high, you're already getting some insulin coming out here, and the sugar's coming on up to the liver, because that's where everything goes that we eat, right? So it goes on up to the liver, and the insulin makes it so that the glucose can be absorbed, right? Like we were talking about before, insulin takes these cells and makes them so glucose can by diffusion, facilitated diffusion, can cross into the cells. And so now it's going to be stored. It's going to be stored in the cells of the liver in a special way. It takes all of this glucose and it turns it into glycogen. Glycogen, I believe. So it stores it as glycogen. And what that is instead of being one glucose molecule, it's a big long string of them, right? A complex molecule. So now it's taken these, it's put all this glycogen together, and it stores it there as glycogen. And as long as it's glycogen, it's locked in the liver. And then the rest of whatever other glucose might get through here will go out to the body and go into the muscles and whatever. So that's what happens when we eat something sweet. All right, system, right? The pancreas, beta cells, release insulin. The insulin takes it, stores a lot of that we don't need because it will be stored in the liver. Some of it goes out into the body for our muscles and everything, so that muscles can store up some energy within each one of their cells. Because the muscle cell doesn't want to have to get the energy when it wants to, when I want to bend my arm up like that, right? Well, it doesn't want to have to get the energy then. It's got to have the energy stored within the muscle cell itself, so it's all ready to go. And so that's what insulin does. It lets this stuff get in these cells. So you've eaten all this sugar, right? And you've got all the sugar coming in there, and you're storing it, trying to tuck it away, but you end up with a high level of sugar. And as the insulin's out there just drawing that sugar level down, it'll drop down and down and down. And if you're exercising and burning energy, you're burning glucose, right? As you burn the glucose, your sugar levels will drop, and more will get pulled into the muscles. But remember, we gotta have a certain level of sugar in our blood all the time, right? So it's going into the muscles, that's all great. But the problem is our brain doesn't have any stored anymore. So we can't let our sugar level keep going down. So you ate something sweet, boom, it shot up here, maybe 140, 150, your blood glucose level, until the insulin brings it down to about 70, right? And when it starts getting low like that, the pancreas does something else. Now I said that in the islets of Langerhans we have alpha and beta cells. Well, now the beta cells release the insulin to bring the sugar level down. Now the alpha cells have got some work to do, right? Beta cells release the insulin, store all of this glucose, get all this glucose into the cells. Now your sugar level has gone down to 70 or so, and now your pancreas is going to say, wait a minute, we don't have enough glucose here. Brain needs constant supply of glucose being brought to it. So the alpha cells now are going to release glucagon, right? So we've talked about insulin. Now we're talking about another hormone, glucagon, which is released by the alpha cells within the pancreas in the islets of Langerhans, right? So alpha and beta cells are both there. And now the alpha cells have got their work to do. Now the alpha cells are going to be released into the bloodstream. It comes on, or into the portal circulation, comes right on up here to the liver. Boom. It takes all that glycogen that was stored, starts breaking it up. The glycogen gets broke up. We've got all glucose, and it gets released out into the bloodstream. That way our sugar didn't go so low that our brain didn't get a supply, right? So that keeps us going. Even though we might be hungry, we haven't eaten for several hours, we don't have to, because we stored it away just for this occasion, because we don't always have food around. In fact, we shouldn't always be eating food, because when the insulin is being released, we're in storage mode, right? If you want to lose weight, you gotta stop eating enough for that insulin to not be released, so that you can get out of the storage mode. Okay, so the bottom line is, insulin brings your glucose level down, glucagon brings your glucose level back up, right? So let's go here, draw a little thing here. This down here is time. This over here would be 70, your lower level of glucose. And let's just make it 120, kind of an upper level, right? So say you're hovering right here at 70, right? You ate something, right? Boom. Your glucose level shoots up past that 120, which is just fine. Gets up past there, and then the insulin there gets going on its work. Insulin from the beta cells gets released, starts storing that glucose away. Boom, boom, boom. It's dropping, right? Then when it gets down in here, down around 70 again, boom. Pancreas alpha cells are going to release glucagon. Boom, it's going to bring that level back up, right? It'll bring it back up around in here. And then you're going to find yourself just stabilizing in there until you eat again, and then you'll shoot back up here. So that's just kind of a little breakdown of what happens when our system is trying to regulate the blood glucose level.